Hello everybody, in this lecture we will be solving 1987 IMO problem number 5. Here is a view of this problem. We would like to show that there is a set of endpoints in the plane such that the distance between any 2 points is irrational, yet each set of 3 points, any 3 points determine a non-degenerate triangle with rational areas. So the side lengths irrational, yet the areas rational for all, and choose 3 triangles possible. Okay, so the key idea here is to focus on lattice points basically, and I have just 2 observations. The first observation is that if you are given lattice points, basically coordinate points with on the coordinate plane with integer coordinates like this, then if you pick any 3 non-collinear so that you get a triangle, let's say you pick this one, and say, I don't know, let's say this one here. So say you get this triangle. I claim that the area of this triangle is either an integer or it is an integer divided by 2. Okay, and the reason is very clear actually, not much discussion needed. So if you focus on the rectangle which contains, the minimal rectangle which contains this triangle, you realize that the area of our triangle is simply the area of the rectangle, which is an integer, right, minus the area of these corner triangles. But each of these corner triangles have an area, either an integer, like in this case, for instance, the area of this top left triangle is 2, versus this one which is just 1 and this one which is just 1/2, right? So this is self-evident almost. So this is the first key observation, and I hope this is clear. So the whole point, the whole idea therefore is to pick the points, the 3 points on the lattice. So we have to pick them on the lattice points so that the areas will become integer rational areas. But then the distances between the points must also be irrational, right? So how can I ensure that the distance between any 2 points on the given the endpoints are always irrational? And for that we can just focus on a curve which such as a very simple example, for instance, y equals x squared, and consider the endpoints defined like this. So the endpoints being k squared on the coordinate plane, where k starts from 1 all the way to n. Obviously these points are all on this parabola, and none of them are collinear, obviously, because the parabola itself is not collinear. And then you can also calculate the distances between any 2 points. For instance, consider pk and let's say pm, which is just have coordinates mm squared. Then the distance between pk pm, the distance is simply equal to the square root of the difference between the x coordinate squared plus the difference between the y coordinates squared, and this is simply equal to k minus m squared is common in both expressions, right? So I can take that out, and when I factor it out, it will come out as an absolute value, and what's remaining inside the square root is 1 plus here we would have k plus m squared remaining. Now the distance I claim is obviously irrational, because for this to be rational we need the inside of the radical to be a perfect square, which is not gonna happen because k plus m is greater than 0, right? So k plus m is definitely greater than 0. So obviously, and in such case, 1 plus k plus m squared is obviously not a perfect square, right? So not a perfect square, and as a result the distance pkpm is irrational, right? So the distance is irrational, yet anytime on this parabola, let's draw the parabola. So we decided to pick up the points 1 1 1 1 and then 2 4, for example, somewhere here, 2 4 3 9 and so on, right? So 3 9. So anytime you pick 3 points, for instance, let's just pick the first 3 points, this triangle is non-degenerate because these 3 points are not so those 3 points are not collinear. And secondly, the area defined here is rational. Just a simple idea is to, for example, consider Pick's theorem, right? So by Pick's theorem, the area of this triangle would simply be equal to area would be simply equal to the number of interior lattice points, I should say, plus half of the number of boundary points minus 1. And obviously this is an integer, this is half of an integer, and this is an integer. As a result, the final outcome is a rational point, versus the distances are obviously not rational. And that solves the problem. Hope to see you guys in our next video.